Consider a computer system with 57-bit virtual addressing using multi-level tree-structured page table with L levels for virtual to physical address translation. The page size is 4 kilobytes, and we know that 1 kilobyte is equal to 1024 bytes, and a page table entry at any of the levels occupies 8 bytes. The value of L is what? So if our virtual address is 57 bits, we know that the page size is 4 kilobytes, or 4 into 2 to the power of 10 bytes, and 4 is also 2 to the power of 2. This gives us 2 to the power of 12 bytes. So if the page size is this much, then when we have to access a particular offset within the page, we will require 12 bits to go to that offset. So now if 12 bits in that whole 57 bits are being used to go into that offset within the page, then how many bits are left to specify the page number? 57, which was the total number of bits, minus the bits for the offset. So 40 bits are left to specify the page number. We also know that the page table entry is 8 bytes. So how many entries can we have per page? This is the page size, 2 to the power of 12 bytes, divided by the size of the page table entry, which is 2 to the power of 9. That means each page can have only 2 to the power of 9 entries per page. So how many bits will we need to index into a page table? That is 9. So only if there is a page, one page can hold only 2 to the power of 9 entries. So we will need 9 bits to index into one of the page table pages. So what will be the total number of levels required? We have 45 bits to specify the page number, and the bits to index into the page table is 9. So 45 divided by 9, which is equal to 5. This will give us the total number of levels. So L is equal to 5. Now a complete description on how it is going to happen. Let me just explain that. So we know that the virtual address is 57 bits. So what is the total virtual address space? It is 2 to the power of 57 bytes. And the page size is 2 to the power of 12 bytes. So how many total number of pages are there in this virtual address space? 2 to the power of 57 divided by the page size. So there are total 2 to the power of 45 number of pages in the virtual address space. So that means that in the page table, there will be 2 to the power of 45 entries. So there will be these many entries, and each entry we have seen that is given in the question is 8 bytes. So now let's suppose that we just had one page table. So in that case, there would be 2 to the power of 45 entries, and each page table entry requires 8 bytes. So how many, and we also know that the number of entries in one page is the page size divided by the page table entry, which is 2 to the power of 9. So to store these many entries, 2 to the power of 45 entries, and there can be only 2 to the power of 9 entries per page, we would require 2 to the power of 36 number of pages. That means these 2 to the power of 5 entries would come in 2 to the power of 36 pages, and each page would have only 2 to the power of 9 entries. Now to find consecutive 2 to the power of 36 pages is very difficult, to find this contiguous memory, and that is why we can have these 2 to the power of 36 pages at separate frames of the memory. Now if there are 2 to the power of 36 such page tables or pages, that means this is, suppose let's say this is level A, and now each of this is giving us the page number and the frame. So this final level A, which is the innermost level, this is going to give us the frame number where the virtual to physical address translation is going to take place. Now for these 2 to the power of 36 pages at level B, I need a page table now which would now have 2 to the power of 36 entries. So, and each of these would point to the address of the page table at level A. You can also check my video on hierarchical page tables, which I have explained earlier. So this is now level B. This level B, the total number of entries are 2 to the power of 36, pointing to the address or the base address of each of these page tables at level A. So if there are 2 to the power of 36 entries in page table at level B, and each page can hold only 2 to the power of 9 entries, that means the number of pages required at level B would be 2 to the power of 27. So if again at level B now 2 to the power of 27 pages would be required. Again, since they would be at different addresses, now we need a page table at level C, which will now, so this page table of 236 has been broken up into multiple page tables and in 2 to the power of 27 pages. So this level C would have 2 to the power of 27 entries. So at level C, the number of pages required would be the power of 18. So that means at level D, there would be 2 to the power of 18 entries in the page table. So at level D, there are 2 to the power of 18 entries. So number of pages required would be 2 to the power of 9. So at next level E, total number of entries would be 2 to the power of 9 and number of pages required would be only 1. So this is how it is going to look like. This is level E, the outermost level, which is also referred to as level 1, and this now needs only one page, and each, so since there are 2 to the power of 9 entries over here, we need 9 bits to index into this page table, and this will give us the address of where we want to go next, which page table we want to go next. From here, suppose if this is the address where we want to go, then within this particular page, the next set of 9 bits will help us index into that particular page of the page table. From here again we will get the address of the next page table. So let's say this is the address of the next page table. For this page table, the next set of 9 bits will help us index into this page of the page table, because we know that in each of these pages the number of page table entries are 2 to the power of 9. Everywhere it is 2 to the power of 9. From here we get the page table of the next level. So this is level 3, which is having 2 to the power of 18 pages we have computed earlier. Now we are going to level 4. Total number of pages being utilized is 2 to the power of 27, and again each of these is having 2 to the power of 9 entries. So again 9 bits to index into this page table. Again we get the address of the next page table and we go here, and again 9 bits to index into this page table. Here is the place where we will finally get our frame number. So this is the frame number that will be used to index into the RAM, and within that frame these 12 bits will be used to go to that particular offset. So these 12 bits are the being used for the offset. So as you can see, we have 5 levels of page table, and at this level 5 we will get our final frame number.